We will set the movement position and speed for the x-axis and z-axis using position control. First, we will set the destination and speed for the x-axis movement. We will specify the speed of x-axis. The destination for the x-axis can be constrained in later time series creation, so we won't specify it here. Click Apply to complete the position control for the x-axis. Similarly, we will select the sliding joint of the z-axis and only set its speed. The target position can be specified in the subsequent simulation sequence. Click OK to complete the creation of the position control. Now, a crucial question: how do we make this object move forward? We will select the transport surface from the position control drop-down menu and set this plane as the conveyor. Choose the vector pointing from the material to the collision sensor as the positive direction, creating it as the transport surface. Click OK to complete the creation of the transport surface. At this point, we have completed the creation of the joint and sensor of the basic physics. Next, we will use conditional statements to trigger the control for starting and stopping the conveyor. This functionality will be implemented using the sequence editor from the resource bar on the left side of the software. Left-click on Sequence Editor. Hold the mouse button down, drag it to the pop-up window at the bottom of the software interface, and release it. Place it directly below the software, as the progress bar is quite long, which makes it easier for our subsequent operations and observations. In the blank area of the sequence editor, right-click Add Operation. We will name this sequence Start Transport Surface. The physics object for the transport surface is the transport surface within the actuators. Look at runtime parameter. We will set its operating speed to 150 mm per second. And we need to click the arrow to show more options. Select the conditions for starting the transport surface. The conditions for starting the transport surface are: the collision sensor does not detect the material and the value of the collision sensor is false. Click OK to complete the creation of the transport surface. Next, we will create a stock transport surface, which involves similar operations as the start transport surface. We can quickly create the same command by copying and pasting. Naming it the stock transport surface. The motion speed for the stock transport surface will be 0. And the trigger condition for stopping the transport surface is when the collision sensor detects the material. That is, when the value of the collision sensor is true. It will stop the motion of the transport surface. Click OK to complete the creation of the transport surface. Now, when the material moves to the position of the collision sensor, we will trigger the downward movement of the z-axis to absorb the material. Select Add Simulation Sequence and name this sequence Z-axis Move Down 10 mm to reach the upper surface of the material. The physics object chosen will be the z-axis position control in the actuators, setting its position value to -10. The trigger condition for moving the z-axis down will also be when the value of the collision sensor is true. Click OK to complete the creation of the simulation sequence for moving the z-axis down 10 mm. Once the z-axis moves into position, we will then trigger the suction cup to grab the material. Create a simulation sequence and name it suction cup absorb material. We will choose the fixed joint as the physics objects. For the runtime parameter, we will check attachment. For the editing parameters, we will select objects in the trigger, where its attachment will be the object detected by the collision sensor. The attachment will automatically recognize the object sensed by the collision sensor. The final condition for the suction cup to absorb is when the value of the collision sensor is true. Click OK to complete the creation of the simulation sequence for absorbing material. After the suction cup absorbs the material, the z-axis will lift up. We can quickly create the upward movement of the z-axis by copying and pasting the previous z-axis movement command. Here, we will set it to move up 50 mm. Thus, the z-axis will move up 50 mm, and we will set its position directly to 50. No modifications are needed here. Click OK to complete the creation of the z-axis moving up 50 mm. Once the z-axis moves up, we can trigger the generation of new material. Here, we will create a new simulation sequence, naming it Generate Material. We will trigger the object source to produce new material. So for this physics object, we will select object source and check the runtime parameter as active. We will check the trigger conditions for this object source to confirm that it produces one object source each time it is activated. After generating the object source, we have completed its creation. Next, we will move the absorbed material toward the material sink, driven by the x-axis. We will create a new simulation sequence and name it x-axis move left, moving it a certain distance. Based on previous tests, the distance from this surface to that surface is 216 mm, so we will name it move left 216 mm. For the physics object, we select the x-axis position control from the actuators. We set its position to the measured 216 mm. And we don't need to set the object selection here since there are no trigger conditions. It will lift up after suction and continue moving without any control conditions. We can then click OK to complete the left movement of the x-axis. After the x-axis has moved into position, we will release the material. Releasing the material is the opposite process of suctioning it. We can copy and paste the suction command and rename it suction cup release material. For the suction cup release, we can remove its connected body and also remove its trigger conditions. Thus, after reaching the 216 mm mark, it will directly release the material. Click OK to complete the creation of the suction cup release sequence. After releasing the material, the X-axis needs to return to its original position to wait for the next material pickup. We directly copy and paste the left movement command for the X-axis and edit it to X return to 0. After the X-axis has placed the material, it will return to 0, and we set its position to 0. There is no trigger condition here. Click OK to complete the creation. At this point, we have finished all the actions in the simulation sequence, starting and stopping the transport surface, moving the Z-axis down by 10 mm to adhere to the material, moving the Z-axis up to a position of 50 mm, generating new material, moving the X-axis left to reach above the material sink, releasing the material, and returning the X-axis to 0, completing the process. Next, based on the previous analysis, we will set these processes as a timeline. Start transport surface and stop transport surface should not have a time duration, as they are trigger conditions. When either the start transport surface or stop transport is executed, our sensor will detect the arrival of the material, and it will automatically move down by 10 mm. Here, we will move the Z-axis down by 10 mm. Starting from here, left-click and draw a line connecting it to the suction cup adhering to the material. After connecting to the suction cup adhering sequence, the Z-axis will raise by 50 mm. Once raised, we will trigger the object source to generate new material. Next, the X-axis will move left by 216 mm. After moving into position, it will release the material. Once the material is released, the X-axis will return to 0, completing the entire action sequence. At this point, we have completed the entire simulation. We can click play to observe if the animation matches the actual situation. Great! We can see that the animation process aligns with the actual situation. Thus, we have completed the entire motion simulation of material handling. Finally, let's review what we learned in this lesson. 1. Analyze the basic components of the conveyor to determine the types and quantities of joints required for the mechanism. 2. Create the units and joints necessary for the mechanism's operation. 3. Create sensors and actuators, implement speed and position control, and complete the preparatory work for motion simulation. Finally, please complete the following homework exercises and practice more after class. This concludes today's lesson. See you next time.